This is the fourth FRQ. This is on kinetics. Its focus is on figuring out a rate law, rate constants, and the activation energy for a particular reaction. If you'd like to try the problem first, you can follow the description down and you'll find a link to the Google document that has the entire problem on it. If you want to try it and then come look at the solution that I'm about to start going through. So in this particular problem, we have two sets of data. We have an experiment being run, 2A plus B turns into 3C plus D. And then we're given various concentrations of A and B in different experiments, and then what their rates are as a result of those concentrations. Okay. So questions one says find the rate law for that particular reaction. Questions 2 and 3 involve finding the rate constants for the reactions at the different temperatures. At the start, we're starting at 65 degrees Celsius, okay, which is 338 Kelvin. And we get a particular rate constant and a particular rate law. As we change the temperature, that rate law is going to stay the same, but the rate constant is going to change. Okay. Now, before we start, there are two ways to do a problem to find a rate law. There's kind of an intuitive approach. It's a little less formal, and then there's a formal approach. I'm going to show you both. So first, I'm going to use this set of experimental data to give you a rate law, and then we'll do the same thing with the second set when we get to number 3. What I would do, or what a lot of people will do, is they'll look for situations where there's two experiments, in this case numbers 1 and 2, where something is held constant. So B is held constant in concentration between experiments 1 and 2. It stays the same. And therefore, the rate is not going to change because of the concentration of B. A, on the other hand, is changing. So what we can do is we can look at how much A's concentration changes, how much the rate changes, and then we can compare those two to figure out what the appropriate exponent is. So from A, for experiments 1, 2, 2, it's going up by 3. It's increasing by 3 times as much. And when that happens, the rate goes from 12.4 to 37.2, which is also an increase of 3. So what that means is that the concentration of A has some effect on the rate, and that's raised to some power. When this is going up by 3, and the rate goes up by 3, you can figure out what that exponent is. 3 to the x has to be 1. So for all of our rate laws, we're always going to write down rate equals a rate constant, and then you're going to put the concentration of every single reactant in that reaction. And then each of those is going to get an exponent. So we start typically by putting maybe an x or a y or a z if we have a third reactant. What we've now found is that the exponent for A is 1. And then when we say find the rate law, what we're really saying is figure out what those exponents are that go with those two concentrations. So we know that A is to the first power on this. So in B, we would have to look at when B changes. Now, none of these situations have A constant, and that makes this a little more difficult. What I'm drawn to is experiments 2 and 3. Because experiments 2 and 3, we see A goes up by 2 times, and B also doubles in amount. So we know from our initial discovery that increasing the amount of A by 2 is going to increase the rate by 2. Okay, so if we go ahead and look here, how much does the rate go up by? It goes up by twice as much. All of that doubling of the rate is accounted for by the doubling of A. Okay? So in other words, if we kind of created another one of these where we said 0.00600, and we kept B the same, 0.0100, we would expect the rate to be 74.4. This doubling will make this double. Then we can look and say, okay, this cuts in half, and my rate doesn't change. So in that case, what that means is that B does not affect the rate, no matter what happens to it. B would be 0 order. Okay? So our rate law then, for experiment 1, would be rate equals K times A to the first power times B to the 0 power. B to the 0 power is 1. That's going to drop out of our equation. We don't need to write the 1, and so we end up with this as our rate law. If we move on to number 2, it says figure out what the rate constant K is and what its units are using the experiments 1 through 3. Okay? That's easy to do. You pick any experiment, 1, 2, or 3. I'm going to pick number 1. and you're going to plug in all of the components. So the rate of appearance of C is 12.4. And the units on that, this is molarity per second, is equal to your constant that we're looking for times the concentration of A. And the concentration of A is 0.00100 molar. So K then is going to be 12.4 divided by 0.001. That's, of course, 12,400. And then for the units, the molarities here are going to cancel with each other, and K is going to have units of 1 divided by seconds, or seconds to the minus 1. Okay, so to find a rate constant is pretty simple. The figuring out of the units can be challenging, but if you plug everything in, it can kind of go pretty simple. Okay, now, this is our rate constant at the first temperature. We're now going to change our temperature to a different temperature. So now it's cooler, 15 degrees, and that would be 288 Kelvin. And we run the same concentrations at a colder temperature, and we get different rates, and they're slower. Okay, so that's showing us that the fewer collisions and less energetic collisions lead to a slower rate. That's expected. So now what I'm going to do is, even though it doesn't ask, I'm going to show you how to do the rate law the other way. Okay. The other way to do it is to kind of start with what you know. You know you're going to have rate equals K times A to some exponent times B to some exponent. Okay, and X and Y are probably going to be 0, 1, or 2. They don't have to be. So what you're going to do is you're going to pick 2 experiments, ideally one where you hold something constant. So we're going to pick 2 and 1 here. And you're going to plug in everything you know from those 2 experiments. So if I take experiment 2, my rate in experiment 2 is 5.34. Okay? I'm going to leave units out to keep it a little less cluttered. I have a rate constant K. And then A has a concentration of 0.003 to some power. And then B is 0.01 to some power. So I'm leaving off the zeros there too. I'm going to take that and I'm going to divide the entire thing by a different experiment, experiment 1. Okay? In experiment 1, my rate is 1.78. Okay? My rate constant is still K. But my concentration of A is now 0.001. And my concentration of B is the same. So if you plug in what you know from the rate law based on the experimental data, that will set you up to be able to solve this, because 0.01 over 0.01, both raised to the y, cancels. 5.34 divided by 1.78 is 3. The rate constants are the same thing. Okay, they cancel. This is 3 to the x. Okay, so you have 0.003 divided by 0.001, both raised to the x power. That gives us this. This we can then solve for x. X is 1. And so then we figure out that rate equals k a to the 1, b to the y. Now what we can do with that extra information is we can do another one with experiments 3 and 2. So in experiment 3, I have my rate 10.7 equals my rate constant times A, which is 0.006. And we now know it's to the first power. Okay? And times B, 0.02 to some power that we don't know. Okay? I'm going to do experiment 2 then, divide the whole thing by it. So experiment 2, I have 5.34 equals K times 0.003 to the first power times 0.01 to the y power. Okay, 10.7 over 5.34 is 2. K's cancel. This is 2. And then this is 2 to the y power. So what we end up with here is 2 is equal to 2 times 2 to the y power. So the 2's are going to cancel. We're going to get 1 equals 2 to the y. What is y? Well, it must be 0. Okay, so then we get our 0 here. And that would be our other way to solve this. Now, let's backtrack. That's not what the question asked. It's just a little way to show you a little extra. This question said, what's the rate constant? Okay, so let's get rid of some of this. So our rate constant here, we have rate equals K times A. to the first power. So again, we're going to plug in our different values. So I'm going to pick experiment 1 again. This has got nice simple numbers. And we have 1.78 molarity per second is equal to our constant times 0.00100 molar. Okay, the molarities are going to cancel. And our rate constant is going to be 1,780 seconds to the minus 1. So we see that our rate constant has gone down as temperatures decrease. That makes sense. Our reaction is slower. Okay. Now, in question 4, it says then make a plot of natural log of the rate constants versus 1 over temperature. So we have this rate constant, which was at 288 Kelvin. We have the other rate constant was at 338 Kelvin, and it was 22,400, I believe, 12,400. So what they want us to do is they want us to plot the natural log of those rate constants versus 1 over temperature in Kelvin to figure out what the activation energy is. So to do that, we can go ahead and take those numbers. We're going to come over here. So we have natural log of our rate constant K, which is going to range along this axis. And then we have 1 over temperature over here, and that's going to be in kelvins. Okay? So what I'm going to do is I'm going to plot those different values. Now, my initial rate constant was 12,400, and that was at 338 Kelvin. Okay. My second rate constant was 1,780, and that was at 288 Kelvin. Okay, so for this, the natural log of this is 9.43. Natural log of the second rate constant is 7.48. And then 1 divided by 338 is 0.00296. And 1 divided by 288 is 0.00347. Okay, so I'm going to plot these numbers here. So I want 9.43 with 0.00296. So I'm going to go to 9. Here's 9. Here's 9.5. So a little underneath this line. We're going to go to 0.00296, which is going to be just before here. And so we're looking at a dot maybe right there. Okay. The second one, 7.48. So now we're looking at just under here, all the way over to 0.00347. It's going to be right to the side of this. So we're looking at kind of right on that point, maybe a little below. So what we can then do is we can make a line of best fit. Okay. And what we want to do from that is find the slope of it. Now in this particular problem, we only have 2 data points. So that's not ideal. Ideally, we would have a set of data points at various temperatures, and we can actually construct a good line of best fit from more data. What I want to say about that is that if you have more than 2 data points, it's very important that you actually find your slope, not from the data points, but from the line of best fit, because that includes all of your data and not just 2 of the points on it. Because this one we only have 2, we're going to use these 2 to find the slope. But what you would ideally do, though, is just construct a line of best fit and then pick 2 points near the end of it to minimize your random error, and then you would use that to figure out your slope. Okay, so for this, well, here's our plot. Okay, here's number 4. But number 5 says determine the activation energy in joules per mole and kilojoules per mole. Okay, so we've done this. So now we're moving on to this. Now, activation energy, the slope of that plot is equal to the negative activation energy divided by R. Okay, so the slope is equal to negative activation energy over R. So what we need to do is we need to find the slope. So the slope is going to be negative, it's decreasing. And all we would do is we would take the difference in y's divided by the difference in x. So we would take 7.48 minus this, and 0.00347 minus this, and we would divide the 2 and get our slope, and our slope ends up being negative 3,820. That negative 3,820 is equal to the negative activation energy divided by the gas constant R, which is 8.314. So our activation energy is going to be this times this, so we can go back to our problem now. So negative 3,820 times 8.314. And we have that negative sign to add in there. And from the negative slope, that ends up being 31,800. Now for the units on this, when we're using 8.314, you're in units of joules per mole Kelvin. And so 31,800 is going to be in units of joules per mole. Okay? And the question says, find the activation energy in joules per mole and also kilojoules per mole. So we're going to divide that by 1,000, 31.8 kilojoules per mole. Activation energy is going to be a positive value. It's how much you're increasing the energy of the chemical system. Okay. And the last part, Food Babe claims the reaction mechanism should be this. Of course, the Food Babe is wrong on pretty much anything involving chemistry. So we're going to go ahead and look at the accuracy of this mechanism with a lot of skepticism, of course. So according to this, we have A and A collide. They form kind of a bimolecular species. And then that collides with B to form our products. Okay, so our overall reaction here is A plus B makes 3C plus D. 2A plus B makes 3C plus D. Oops. Sorry. Okay, so what we can tell about these mechanisms is from which step is slow and which step is fast, we can get information about the kinetics. So the fact that this is the slow step means this will tell you what your rate law is going to be. So this tells us that our rate law is going to be rate equals K times the concentration of A2 times the concentration of B, because in the slow step, that's where your reaction gets kind of stuck or limited by. So the more of this you have and the more of this you have colliding, the faster that step is going to be. This step doesn't matter as much because that just goes to set up this step, but this is occurring very quickly. Now, we don't want to have A2 in our mechanism because that's not actually a reactant or a product, or a reactant. So we're going to actually get rid of that and replace that with these two A's here. So because the first step sets up an equilibrium, we can say that the forward rate of these two turning into this is equivalent to the reverse rate of this turning into this. So we can actually go ahead and replace this and end up with A squared B. This is what the mechanism would be, the rate law would be, if this were the mechanism. But from our experimental data, we know that the actual mechanism is not this, it's rate equals K times A. So the fact that the mechanism here gives us a rate law that does not match our experimental rate law, we know that this mechanism is incorrect. Okay. Now, in the last part here, we're going to assume that it was correct, just for fun. And it says, draw a reaction energy diagram for this proposed mechanism, label the chemicals involved. Okay, so your reaction energy diagram, you're plotting the energy of the chemicals versus the reaction coordinate, what's going on in the reaction. So at the beginning, we have our reactants. So we're going to have 2A plus B. And then the two A's are going to collide. They're going to stick together. So we're going to have kind of a little there. Then that intermediate, A2, is going to collide with a B, and we'll form our products. So at this point right here, what you have is you have your A2 plus your B. And at the final point, we've converted things into C's and D's, 3C plus D. Here we're going to have transition states, or activated complexes, where we've kind of begun breaking things apart, but not yet kind of forming these things together. So at this point, we might have a kind of a triangular pattern of two A's and a B, something of that nature, but some kind of high energy species. The other thing that's really important here is that the activation energy for this second step, called the EA2, is larger than the activation energy for the first step because of this proposed mechanism. The fact that this is slow means that this needs to have a higher activation energy for the second step than the first step. Okay. Now I don't know whether this is an endothermic or exothermic reaction. I think I've got it slightly exothermic here. We don't know from any of the stuff that we're told, but that's just kind of happened to be what I drew. Okay.